Okay, so I guess we can get started. So, welcome to the Friday Afternoon Physics Colloquium. It's my great honor to welcome Dr. Michael Tobar, who's actually an IEEE UFFC Distinguished Lecturer. His bio is long and illustrious. Professor Tobar leads the Quantum Technologies and Dark Matter Research Laboratory at the University of Western Australia. So the lab is part of two nationwide Australian Research Council centers, the Center for Engineering Quantum Systems and the Center for Dark Matter Particle Physics. There's broad research interests that include the disciplines of frequency metrology, precision and quantum measurements, low temperature, condensed matter, and quantum physics. So over his career, he's developed a variety of measurement tools that have allowed investigations in many areas of physics and engineering. And he has over 300 refereed journal publications, 12 patents, on precision radar and detectors. He also leads the well-known Oregon Axion Dark Matter detector collaboration in both centers. And most recently, he's been working on some very interesting stuff on the electric Carnot Bohm effect, which is what he's going to give a talk on at the March meeting. So let's welcome Dr. Tobar. Oh, did it just turn off?
Yeah.
Oh.
This is informal. We've already been discussing the footy, so we call football footy in Australia. Short English. But anyway, as I'm involved in these two centres of excellence, engineering quantum systems and dark matter particle physics. This is our team. There's a few academics, postdocs, and we've got a bunch of students, graduate and undergrads, working with us in various ways in our experiments. You can actually do a virtual tour of our lab if anyone so chooses. You can see everything in there. Here's an example of the equipment we've got. We have these extensive experience with low temperature systems. Used to be wet systems when I was a student, now it's cryogen free. We've got a bunch of systems that go just below 4 Kelvin and a dilution bridge that goes to millikelvin. You see they got names. There's various people in the labs have named these. No one's named the last one. So it's just called bridge free.
Vanilla ice. Vanilla ice.
So we've got a bunch of magnets, so we can do stuff with magnets, and a large lot of microwave equipment and precision equipment. So I'm going to talk first about the technology. We basically do measurements with photons, phonons, and spins. We also use test fundamental physics for precision measurements, and we're looking at dark matter, trying to look to do precision measurements to see if we can detect some forms of dark matter. We're also interested in looking for high-frequency gravitational waves, and we're looking at theories of quantum gravity, looking at precision measurements. We could do Lorentz violation experiments, which we've done in the past, or maybe look at does large masses affect quantum mechanics. First I'll say, there's probably a bunch of theorists here, physics is an experimental science. And does anyone know Grace Hopper here?
Sure.
Yeah, I knew you would know. You seem to know everything. So, Grace Hopper is famous, and usually it's the younger generation hasn't heard of her. But she had this quote: "One accurate measurement is worth 1,000 expert opinions." Okay, and that's like one measurement, and the 1,000 expert opinions are all those theory papers, right? So, who was Grace Hopper? She invented COBOL. Have you heard of COBOL? Yeah, a lot of mods. Young people up the back. Have you ever heard of COBOL? It's a computer program. Back in the old days when we had these tapes and floppy disks, you'd have to compile it. Yeah. So it's probably still being used, like Fortran. But what impresses me here is that someone who's a computer scientist realized that measurement was valuable, because if you have precision measurement, you avoid numeric errors or something. The more precise you know your input, the better your outputs will be. That's the whole point. So we do precision metrology. What that means is we're going to measure some observable. It's usually frequency, phase, energy, something like that. some sort of precision measurement, and you have to have a system to do it. So you can use photons, you can use spins, and you can use phonons, acoustic systems. So we've done a lot of these various experiments over the years. This is a sapphire resonator, which is where I sort of started. So it's a microwave cavity where waves bounce around the edge in whisper and go mode. This is a tunable resonator that looks for dark matter, just an empty cavity with some sort of tuning mechanism. And then we might use spins, like in a hydrogen maser you have spin flip transition. In an atom, which is hyperfine, this is a magnon system, or we might use spins in solids. Like they're typically used for qubits, spins in solids. And when you start looking at solids, that becomes condensed matter. Or acoustic systems. These are bulk acoustic resonators. These are actually quartz, and these work as a quartz oscillator. But you can also do more than make an oscillator out of these things. So my work started working on these sapphire resonators. Sapphire has a permittivity on the order of 10. It's anisotropic, but it's very low loss, electrical losses and mechanical losses. So you can create microwaves with very high Qs on the order of the line width of the resonance to the resonant frequency is greater than 1 billion. And this is what the modes look like when you solve them in electrodynamics. They sort of travel around the circumference. And that's what I started with when I was a student. And I modeled the resonances in these. And then we use them to build these oscillators. They become the resonator in an oscillator. You create a feedback circuit and make it oscillate on the resonance. And you build the circuit which tightly locks it. In microwaves we call that a pound system. Maybe you modulate and it's pound. If any of you guys do optics, it's pound Drever Hall. It's called after Jan Hall from Boulder and Ron Drever from Scotland, who worked out how to do the equivalent pound systems in the optical. And when you lock them using this technique to the resonance, you can get frequency stabilities of parts in 10 to the 16. So that's a very high precision on a frequency you can use to look for certain things. They also have become commercial. You can buy these things in Australia and France. People are making these. So what we did first with these oscillators, why they became important, is because atomic clocks work. I don't know if any of you guys know about atomic clocks, but what happens is you shoot some atoms through a microwave cavity, and there's a fountain, and they're called fountain clocks, and then the atoms come back down and they get pulsed again, and you get these things called Ramsey fringes. And in the middle, the first Ramsey fringe in the middle, the narrower you make that, the better stability your clock. So Ramsey won the Nobel Prize. There's lots of Nobel Prizes in this area. The first, that's why they're named after him. And so what you do is when you pulse it, you're not measuring it for a certain amount of time. And there's nothing magically quantum mechanical about these Ramsey fringes. They're just the same as aliasing. If any of you guys have done communication theory, when you're not measuring something continuously, you get a sync function with sidebands. And that's all it is. It's exactly the same physics as that in communication theory. But what happens, because of all those extra sidebands, when you lock to that middle lobe, which is high Q, those extra lobes make you susceptible to the noise in your interrogation oscillator, which pulses the atoms. And what it means is that a normal quartz oscillator, which I showed you before, it doesn't have the frequency stability to get to the quantum noise level, what they call quantum projection noise. And only the sapphire oscillators we were building in that time were able to do that. So that's where we first got, I guess, well known. We put these oscillators in Paris Observatory, and then for a long, long time, including up to now, it's been the heart of all their timing. And with these propagated around the world, and you really need these. And now, these days, you have qubits, and you can use these atoms as a qubit. You might have heard of a qubit. Well, this one is in Sydney. They use trapped ions, ytterbium ions trapped, and if they use a quartz oscillator, they don't get high fidelity on their qubits. They need to use a low noise oscillator. oscillator. And if they use a low phase noise oscillator, they will get an order of magnitude better fidelity on their qubit operations when they make a quantum computer out of trapped ions. So low phase noise is very important. It was important back then, and now we're getting all these new quantum technologies. In the US, they have 5. I don't know if you know about the quantum centers here in the US. There's 5 of them getting funded at $25 million a year for 5 years. I had to review some of them, and I couldn't believe the money. So this is ytterbium ions, and they leave notes. So these low phase noise oscillators are really important for all these new qubits. And where it all started for me was when I was doing this. This is everyone. You've all heard of these gravity wave detectors. Now, some of you guys mightn't know what this is if you're not old enough. But this is called a Weber bar. This after Joe Weber, who started gravitational waves, even though he had a few wrong sort of theories. If it wasn't for him, I probably never would have started. So we built one of these in Australia, and this was my PhD project, actually. So these are actually sensitive to gravity waves, and they were built before the interferometers. And what we have here is a very high acoustic system, a big 1.5 ton niobium bar, coupled to a flap to amplitude the vibrations. If a gravity wave hits it, it will resonate. And then we have to build a low noise readout. And to build that low noise readout, we have this reentrant cavity here, which is like a post, which makes a capacitance, and it modulates the capacitance, and the length of the post is an inductance. So it's a lumped LCR circuit, and it enables you to measure this. And then you have to put a very low phase noise signal in here, so you don't swamp the signal. Then you have to read it out. And the readout uses phase detection, which uses a mixer. And we realized that if you have the mixer has a lot of noise on it. But if you amplify the signal beforehand, the noise of the mixer doesn't matter. But if you put power into this amplifier, it saturates and creates a lot of flicker noise. So we built this microwave interferometer to, even though you have the signal, we get rid of the carrier. And that worked really well, and we had one of the most sensitive gravitational wave detectors in the world for a while, though it didn't detect gravity waves. But it's basically optomechanics before it became trendy. This was an optomechanical system. We did a lot of firsts. We didn't have the language, but we did a lot of firsts. It was basically a huge optomechanical system. And then, so we developed this carrier suppression interferometer, and we realized we could use it to cancel noise in oscillators. We used it was more general for this readout. So we built the mixer detects phase of a microwave signal. But what we did is so this would be used as a phase detector of your microwaves. And so what we did is we built in this interferometer beforehand, and we were able to build this readout system, phase readout system. When we first built it, it's a factor of 1,000 better than anything that had been done before, a factor of 1,000. And it was published in 1998, but we actually did it in 1995. This company took the technology and delayed our publication because they didn't want the world to find out what we were doing, and everyone was buying these oscillators, I think, of this company in Australia because they were 1,000 better noise than anything. All the defence companies were buying them, and it's doing really well. So this was a major breakthrough. And what happened? And this was the devices they sold with low phase noise oscillators. So from our fundamental research, we made this really practical device just by realizing our readout could be applied to the cancelling noise in oscillators as well as detecting gravity waves. Anyway, we had a lot of patents, and in the end, Raytheon just bought out the company because they needed it. And as soon as Raytheon bought out the company, they didn't sell these oscillators anymore. They just kept the technology to themselves. You couldn't buy them anymore. Now that the patents have run out, there's another company in Australia trying to build these things again because they're going to be important again for all these qubit operations. And really clocks and things like that. So Raytheon bought it out, and now there's this resurgence. And so in all the defence radar that Raytheon makes, it's got our inventions from Perth. It's all our inventions. last time they're still using it. And now we build these cryogenically when we want to build low noise oscillators cryogenically. We're publishing on that. But then there's these defense control things that we don't know what's going to happen with all that stuff. So that was the work we were doing. And when you look at sapphire, there's two properties. I've actually talked about two different ways of making a high purity signal. One is with low phase noise, so the spectral sensitivity out at a kilohertz, where radar is important, is really good. And the other one is these high stability oscillators, which are low temperature and pump the atomic transitions. They were at low temperature, and that was highly frequency stable, and that means your long-term stability is really good. But the reason why they work was like a miracle, and this led me into researching condensed matter physics, because when we cooled these to 4 Kelvin, and we got around 4 Kelvin, the temperature dependence froze out. So this is what happened. The permittivity of the lattice changes with temperature, and there's some spins in there that you can't help, they're just impurities, and they have a susceptibility, and that creates this turnover point. So if we can control the temperature to this temperature here, we get a very stable source. And without this would never work. And here's an example of a measurement that shows this temperature turnover at around 7 Kelvin. And nearly every sample we got either had a turning point between 2 and 10 Kelvin. And it didn't matter what the impurities was, or more or less as long as it was fairly pure. And this is because this turnover point had a t to the quarter square root 1/4 dependence. So it just happened to be around here. It was like a miracle. So so I call it the frequency temperature miracle. And so these spins created this very nice property for our sapphire. And so that led us into investigating spins in solids, because we wanted to understand the physics behind why these spins were working for us and when they don't work. And you know, we could even get 3-level systems and make a maser with all these residual spins, parts per billion, Fe3+, and that's what this shows. This is the most pure sapphire you can get. You can buy it in Salem in Massachusetts, you know, where they make the miracle crystals, you know, Salem. It's where they're famous for witches, isn't it? So that's why it probably worked. You know? Anyway, so here's some spectroscopy. We apply a magnetic field to this sapphire, and this is frequency, and everywhere along here is one photonic mode in the sapphire. And then as we pass through, when we apply the magnetic field, we see spins go through the photons, we see the interactions, we can put dots. And then like when you're a kid, you can join the dots. And we can then work out what all the spins are. This could be a puzzle in the newspaper. What spins do you have? Join the dots, you know. So that's basically what we did, and we could see all these spins. And very clearly, especially at low temperatures, this is a millikelvin where the susceptibility becomes really large. And this is what it looks like. In the sapphire, we'll have the whispering gully modes, one right-handed, one left-handed. There's 2 of them, they're degenerate. But what really happens is there's backscatter, so it's one scatters back onto itself, and mirror symmetry is broken, and they split with a coupling between them. So at zero magnetic field, you get 2 modes at one frequency split due to the imperfections or the crystal lattice causing backscatter. Then when you add the magnet, you see all these spins go through. You can see some hyperfines here. You can identify them all. And the very interesting thing is, one mode interacts very strongly with Fe3+, and the other one doesn't. So that's time reversal symmetry breaking, where angular momentum is important in the interaction with the spin, where it's only interacting with the one that conserves the angular momentum. So that was an interesting find. And then what you find at low temperatures, I told you we had Qs of over 1 billion, very narrow line widths, but when you go to low temperatures, all those spin levels unpopulate, and then they become loss mechanisms. And so as you as you get lower in power, the Q gets worse, and you have to, and if you saturate those spins, the Q goes up. So this is a problem in all quantum computing sort of low temperature physics, is that there's all these two-level systems creating extra loss at the single photon level. So we've studied lots of cavities in our lifetime, in my lifetime, yeah. And so that I've just talked about this one, and I've talked a bit about this one, which is a reentrant cavity, which is a displacement sensor. If this modulates, it will change the frequency. I always wondered what would happen if we had more than one post, and then we got COMSOL and we could model it. So then we modeled all sorts of topological structures. There's one we call chiral symmetry. We can have left and right-handed structures. We built tunable structures that would couple to NV diamonds, for example, and other structures which were hollow, which we could couple to some sort of spins in solids here. And more recently, we've developed these resonators, which are like Mobius strips and twisters in them. I don't know if you guys know about helicity in photon modes, but in a resonator, no one's ever built a resonator with helicity. These are the first microwave resonators that have helicity, a non-zero E dot B term. And they're like Mobius strips, they're twisted, and the boundary conditions cause non-zero helicity across a volume. Usually you see it in edge states, not in a volume. So this is really new work that we've been doing.
What material is it?
This is 3D printed aluminium.
So why is it called an anion cavity resonator?
Aha! I'll tell you that later.
All right.
But it's a symmetry. It's a symmetry.
In particle physics, anyons are particles that sort of bridge the gap between fermions and
Yeah.
bosons.
So the geometry of this is in between fermions and bosons. I'll explain. It's just geometric and I'll explain that later.
Okay.
So yeah, that's exactly that, right? So we also, when we got to more posts, this was very interesting. We patented this idea. With a reentrant cavity, you have a capacitance here and an inductance there. So what happens when you get more than one post? Well, if I have one post, there's an electric field in here and magnetic field outside the post. If I have two, I can have the electric fields in phase. If they're in phase, these two posts acts like one post and all the field is outside. But if they're out of phase, the RF field gets put inside between the posts. So this was really the first way I've seen that you could make a cavity, a microwave cavity, and you could always put the electric field in a really small spot, but not the magnetic field, because the magnetic field is usually outside. But here we were able to put it, so we got this sample of YIG, and we put it in here, and we put all the RF field in there, a really high concentration, so we got huge couplings between the photons and spins. In other words, we made cavity polaritons, and we sort of patented that. And this was some of the results where we've got a mode, what we call our dark mode and bright mode, the one that's bright to the spins and the one that's dark. And then when we change the magnetic field, we see the G factor changing the spins. The first mode of our mode, it's called the Cattell mode, doesn't interact at all, just passes through because there's no RF field. But the second one is huge couplings. You get a splitting of these modes of the order of gigahertz. Okay. Now, I don't think we're still today, now we've got our best result is about 6 gigahertz. And this paper is now my highest citing paper. Yeah, because it was a bit of a breakthrough on how to get strong coupling and with spins in a cavity. And we also, we coupled to diamond centers, and we could make these brick, that was at 20 gigahertz, we could make them lower if we wanted, so we made it at 6 gigahertz and we got strong coupling with P1 diamond centers. And here's an example of our chiral system where we showed how we can then have more than one post and we can virtually make what we want. And we could make it reconfigurable if we wanted, if you could just manipulate these things. Anyway, I won't get into all that. So here's what we call the anion cavity resonator. It's still under review. So this is the geometry part. So if we have just a normal ring resonator, then that has boson symmetry. And if we twist it and make it into a Mobius strip, that has fermion symmetry. So let me say what that means. With the boson symmetry, there's no difference between spin, what we might call spin up and spin down, so there's no chirality. In the fermion symmetry, you have left-handed and right-handed, and one cannot be mapped onto each other. So it's the chirality, you cannot change the handedness. So that fermion geometry. I'm not saying that the modes inside of fermions are bosons, this is just the geometry. So the fermions come in two chiralities called left and right, and bosons do not. So let's have a look at that. Say if we have a rectangular cross-section, it goes back on itself with that sort of boson symmetry. If we twist it 180 degrees, then that comes back as negative on itself. That's fermion symmetry. But an anion cavity is when you change the geometry. It doesn't have to be this geometry. We could have a triangle, or you can have a square. So these are the group of regular convex polygons. You could have 5, you can have 6. And as you go up, it gets approximated to a cylinder. So what we can do then is that we can twist that back on itself, and it will be anion geometry. So that's why we call it an anion cavity resonator, because the geometry is like this anion geometry, not fermion or boson. But we found that if we want to maximize this effect of this geometry, when you twist it, then you want the lowest order you can get. Because as you go up in order, if I had a cylinder, nothing would happen when I twisted it. Okay. So we worked out that this would give us the best sort of, eventually after 2 years we worked out that we were looking at rectangular systems. And so what happens in these resonators is very interesting. If we have a resonator with a certain aspect ratio, the best aspect ratio is 1. And the same with a waveguide. If I have a waveguide, I usually never make it square because there's degenerate modes. I usually make it rectangular. And that way I get a single mode traveling through it. So you can't buy a waveguide which is square. But in what we're trying to do here, we want the degeneracy, we use the degeneracy. So what we do when we have aspect ratio of 1 with a square or a triangle, then we have degenerate modes. So here we've got degenerate modes, but then when we twist it, we get this strong coupling between the two modes. They separate. And what happens, we change basis. We no longer have T and Tm mode basis, we have Te plus or minus Tm basis. And that Te plus or minus Tm basis has chirality. We have a left-handed chirality and a right-handed chirality. And that's it took us 2 years to understand this when we started doing it. We didn't understand it at first, but it was, once we realized what happened, it was like, oh yeah, that's sort of obvious. But, so this is really interesting. If we don't have quite the 1 aspect ratio, you still get a coupling, but it's not as strong as on here. And so these become like helical states with helicity, which could be vortex modes or circular polarized modes, left-handed, right-handed. That's the way you do it in optics, but this is the first time anyone's made a resonator over a volume with these chiralities in it. And I think it's going to be, in the future, very interesting, a whole lot of applications. So we call it twisted anion cavity. And we got this one built, but when we drilled into it, it was solid, and we couldn't make it. So we had to make it in 2 halves if we want to do this Mobius type one. But we made these, and we measured the modes in them, pretty high Qs, a couple of thousand at room temperature, but with superconductors, so we're going to cool them down, and we should get good Qs. And our theory and experiment matched up perfectly, so we understand these well. We understand them. And the reason we did it is because we know that helicity is defined as E dot B of the mode. The mode has non-zero E dot B, it's an imaginary E dot B, and that's what you need to be sensitive to axions, which I'm going to talk about. And so this is a new way to measure what's called low mass axions. And that's within the bandwidth of the oscillator. No other experiment can do that. So you just, it's self-sensitive. I won't get into all this stuff. I don't know if you guys know what axions are, but I'm going to tell you what they are soon. So that's the technology we've built, and now I'm going to talk about searching for new physics. So one of the big experiments we're trying to do is look for dark matter. We're part of ADMX. We work a bit with ADMX. We're part of the collaboration. We all know that there's this dark matter around us holding the galaxy together. If it wasn't for this dark matter, all the stars would fly off. So there's this extra sort of gravitational force keeping the structure together than there should compared to the rotation curves. And then there's also, when you look at gravitational lensing, you can see the luminous matter and the center mass of the dark matter is totally different. So there's a whole lot of different measurements that suggest that there's dark matter out there. And if this dark matter is there, then it's all around us right now, and we're traveling through it. And because it's all around us and we're traveling through it, we can, if we know what it is, we can come up with experiments to measure it. So the question is, does dark matter interact with standard model particles, and can we convert dark matter into standard model particles? And that's what people are trying to do. Can we use precision measurements? And that's what we try and do. But dark matter is can be anywhere from whatever, I don't know what Z is, but ZeV up to 30 solar masses. This is a huge mass range, the availability. So we have no idea what this particle is. We have no idea what its mass is. Should we be looking for it? So our technology can look down here because we do precision measurement. You might know all these experiments underground and look for WIMPs and everything are up here and fail to measure a particle that explains supersymmetry. So the idea for the WIMPs is that supersymmetry, and the idea down here is for this light dark matter is the prime candidate is the Axion, because it should because I don't know if you guys have heard of the Axion, but it somehow solves the strong CP problem. There's a strong CP problem where the neutron, which is neutral, should have a dipole moment. And the dipole moment is being measured to be 10 orders of magnitude smaller than what it should be if you use a naive calculation. Okay? Now, so that seems to be a problem. For me, it's not a problem because I'm not a theorist. For me, it makes sense that EDM is zero because plus and minus charge want to go together. But it also should be created in the early universe. If this axion exists and you do the calculation, it is created in the early universe. And if some calculations suggest that it could be produced enough to be all this dark matter. So this is the best candidate for the low mass regime, where the best candidate for the WIMP regime is the supersymmetry, which they fail to exist. So axions have become trendy these days. And these, if you're looking for them, they will appear in your experiments via wave phenomena rather than individual quanta. Here you get recoils in individual quanta. Here you're doing measurements on what looks like rather high precision measurements on waves, like a gravity waves experiment. So you need precision experiments for this. And so we're part of ADMX and we've got our own experiment organ. You might have heard of ADMX in Seattle. So the generic experiment to detect dark matter, first you've got to have some theorist tell you what the dark matter is, then the experimentalist can build an experiment, do calculations and build a physics package which has high sensitivity to that dark matter. And it could be sensitive to different types of precision experiments. And so you've got to design a physics package sensitive to whatever dark matter. There's also a scalar dark matter called a dilaton, which is quite popular. And we've got to know how it interacts and optimize the signal, and we've got to reduce the noise. And the fundamental noise is quantum noise, so in the end you might have to do quantum metrology if you run out of ideas to increase the sensitivity. And so what is the Axion and why it should exist? You might have heard of Frank Wilczek. He's the one that came up with the name for the Axion, and he told me that he named the Axion after this washing liquid. I don't know what it washes. It looks like it washes dishes or something. But Apparently it can clean the strong CP problem. And he's still active in these fields in MIT and Sweden, and still trying to prove that. So he predicted, he was one of the people who predicted the Axion. Weinberg, I think, was the other one. And then the person who came up with the idea to actually measure it was Pierre Sakivi. And Pierre Sakivi is part of the ADMX collaboration, so we work with him. We're working with him on some stuff at the moment. And so this is, what is an Axion? Well, the Axion can interact with many standard model particles, but if it interacts with the photon, it's a so-called two-photon transition. So it's a chiral anomaly, like the muon. And so what happens is that you can use this to detect it with photons. So you'll have one Axion over here, and then one of your photons, usually what Pierre Sakivi invented was that would be a DC magnetic field. So that means your gamma 1 photon will be just virtual photons at 0 frequency, and therefore your Axion mass should convert totally into this second photon frequency, and you get a real photon out if the Axion exists. And so you measure that with a cavity. You need a high Q cavity to boost it, and because we don't know the mass, we need to tune it. But it also has to have the property E dot B is non-zero, so the B field of this must be dotted with the E field of that, and so that limits the amount of modes you can use in your cavity. And it means the modes that you can use are the ones that don't tune with length and only tune with radius. And how are you going to tune a cavity by changing the radius? It's very impossible. So what they do is they stick rods in there and they stir and push the mode around, and that tunes it. So it's pretty brutal. It's not elegant, but there's no other way. So the Axion is predicted to be produced in the early universe, and there's these models. They seem more strongly coupled than the QCD Axion, which is predicted from the strong CP problem. But these days, theorists have really invented, they can make the QCD Axion be anywhere now. They call these Axions photophilic and photophobic, whatever they are, and they can be anywhere. So theorists always put in extra degrees of freedom and make things useful so you can do an experiment. So that's very useful. So there is one model that predicts the mass of the Axion to be up here, and that's where we're looking. We're the only current experiment looking up there at the moment. Though there's a few other experiments being proposed. We've got this nice dilution bridge funding for that to do this experiment. And our first scan was published last year in Science Advances, and where we looked in the mass range where lattice QCD predicts the Axion to be, and this smash model. So right where we're looking where, as an experimentalist, I prefer to look where the theorists say that things are, because there's more chance of just looking anywhere else, you hope. So this is what it looks like. This is our tuning curve. You can get some node interactions, crossovers from other nodes. So we tune this TM010 node in this cavity by stirring this rod and pushing the mode pattern around. And we use that to do our scan under 11 Tesla magnetic field. And this is our first phase. These parts that we didn't look at were because of the mode interactions. We sort of know how to deal with them now. We worked out that if we just put a sheath of Teflon around the tuning rod, we can shift them all away, but we didn't bother doing it because we're going to come back and do it more sensitively in the future. So our run plan, we've done this run and we're now working towards this run 1B, and this is our plan for the future. I won't get into the nitty-gritty details. It means we have to invent what's called a single photon counter if we want to get down and measure these model bands. But at least we can put limits on these ones that are predicted from the early universe. The interesting thing is that these Axion detectors are also high-frequency gravity wave detectors. There's this magnetic conversion called the inverse Gernshtein effect. So if I pass a gravity wave through a magnetic field, it will convert to a photon, just like an Axion. So that proposal's been around, and what some clever people did recently is they worked out that an Axion detector actually, there was this paper that's published in PRD now, which they did a calculation where they showed that, that the way you would convert a gravity wave in the Axion cavity derives a similar effective current to what the Axion derives. So your strain sensitivity to gravity waves is equal to this so-called theta angle in Axion electrodynamics. They're of the same order. So after that calculation, we now realize they show that there's ADMX in our detector. They showed that all these Axion detectors were actually sensitive to high frequency gravity waves. So if all we have to do is when we're doing our data analysis is look for a different type of signal. Dark matter signal that we should see from the galactic halo is like a narrowband noise source. Gravity waves has a different sort of response. You just have to do different filtering. So this is the mass behind this calculation, where when we're doing Axion electrodynamics, we have this theta angle, which is your Axion theta angle, and it's the coupling to the Axion times the Axion field, and here's the strain sensitivity. So what we did is that means we could look for high frequency gravity waves with our stuff. And there is a motivation. Most of the gravity wave community says there's nothing up there. There's nothing at gigahertz or megahertz. But there is some calculations due to exotic sources beyond the standard model. So it's worth having a look if you're sensitive, in my opinion.
I have a good question. You say the axion and the gravity wave are similar range, then how you distinguish them?
Yeah, because the signal's different. So if I'm looking for the galactic halo will have, the particle will have a certain mass, but because it's virialized, there's all the kinetic energy and it's all, it's like narrowband noise source. So the line width of the galactic halo is a part in 10 to the 6. So the signal that you're trying to look for amongst the noise is like a narrowband noise source. It's like a signal with a part in 10 to the 6 line width.
You mean some like a Gaussian, some like a Lorentzian?
Yeah, it's Maxwell-Boltzmann distribution. But you can approximate it as a Lorentzian if you want. Yeah. And that's what we do. We approximate it as a Lorentzian, and you're not going to be far off. But it's where the gravity waves will have a different, depending on the source. You like what the gravity wave people do, they use filters. You use a different filter. So to see it, you have to use a different filter. So we have to assume, okay, this is like a chirp. Let's put a chirp filter in and search for chirps in our Axion signal and see if we can see a chirp. Or maybe it's just a burst. Let's do a burst type filter, see if we can see a burst. So yeah, the gravity wave signal will be nothing like the dark matter signal, nothing like it. Yeah.
Is there a reason that we have to stick to astrophysical sources and not possibly like artificial sources generated in the lab for gravitational waves?
Not in principle, no, but in practice, it's just very weak. So this is where all they're up, and there's all these different technologies, including the axions, and we also have these Bohr cavities, Bohr resonators that are sensitive up there. So I did this paper just recently, and with my group, it's helped. So what you see here is, so the way that gravity wave detectors compare each other is through strain per root hertz. If I just want to not consider the signal and just consider instrumental noise, I will plot LIGO as strain per root hertz. And what this means is your transductance and your noise taken into account, but nothing about the signal. And this is a LIGO strain per root hertz. I can now do the same with Axion detectors, where it's theta angle per root hertz. And you've got ADMX here, which is narrow band like a bar, and I can tune it. We've got this Bohr resonator, which we call MAGE, and that's just like a resonant detector, so it's very narrow band. And these are some broadband Axion experiments. So now I can compare it to model the one bigger, and I can compare Axion detectors without knowing the signal source. So I did that just to show the Axion community that we could be like the gravity wave community and do that. So the last topic that I want to really talk about is this interesting stuff that we do with acoustic resonators, looking for high frequency gravity waves and testing quantum gravity. So we're looking at using these Bohr resonators. So bulk acoustic wave resonators are very interesting. They're basically, each of these resonators will have a radius of curvature, and this has phonons in them, and they act like a February cavity, so they're in the middle. So here we have, we're looking down on a Bohr resonator. Most of the vibration's right in the middle. That means there's no loss. This is we put a 3-point suspension, and you get very high acoustic cues because you've got no acoustic losses. And when you go to low temperatures, you get to 10 to the 10 Q, which is extraordinary high Q for an acoustic system at megahertz frequencies. So we're talking about 5 to 1,000 megahertz. So these are used as oscillators with 10 to the minus 14 stability, not as good as the Sapphire, but they're pretty good. At room temperature, they have a Q of 10 to the 6 here, they're 10 to the 10. And so we've used these for a bunch of fundamental physics. And what makes it even easier to use is that they're piezoelectric, so you just need to put capacitor plates here to get charge on them from the acoustic oscillation. You can pick out the signal quite easy. And there's a high density of modes from up 1 to 1,000 megahertz to choose from. So what we did is we reread this out with a squid amplifier, and we looked for high frequency gravity waves because this is actually a resonant bar system. It's actually sensitive to dilaton dark matter as well, so we can look for dark matter. And we first proposed this in 2014, and in this paper we proposed it. And so if we see anything here, it might point to new physics outside the standard model. And there's these sort of proposed sources that you could get. So what did we see when we ran this? So usually we're measuring just the thermal noise. So this will be with a lock-in amplifier, just measuring the thermal noise amplitude. But we did see 2 events in 153 days. We saw 2 significantly strong rare events in 153 days. And because we saw, let me just go back to tell you about these events. So we got the first 70 odd days of data, we saw 1 event, but we had the ability to monitor 2 modes. So we'd look at 2 modes. The first mode was at 5.5 megahertz, and the second one 8 point something megahertz. And we saw this event. So this is the characteristics of this resonance. Like it got a kick, and it can't. And this is really well shielded. There can't be anything up the chain because it's got the transfer function of this. So something had to excite this. But it didn't occur in the 8 megahertz mode. So we stopped the experiment, and we got 2 modes excited around 5 megahertz. One at 4.9, one at 5.5. The second event was seen in both. So that tells you something about the spectral spread of the event we saw.
Mike, can I ask a quick question on one previous slide just before that?
Yeah.
Is that the magnetic field on the left side there, of that equation?
No.
The B's?
No.
What are those B's? Because I noticed on the right side you got a Riemann tensor, so I imagine that's the gravitational wave.
Yeah. So that's just probably the eigenfunction of the accelerator of the mode here. So this is just the second order equation.
So do we interpret that as gravitational wave on the right generating something
yes.
electromagnetic
Yeah,
on
that's
the
a
left?
forcing function, yeah.
I see.
Exactly right. So we've seen 2 events over 153 days. What are they? So now we have to build more than 1, and we have to look again and see if we get correlations in the 2. If we get correlations in the 2, then that will be interesting. If we don't, then we can say maybe it's something just relaxing in this system. Maybe it's an electron just discharging, or a crystal relaxation or something, I don't know. But it also could be cosmic rays, but if it was cosmic rays, you'd see more, and not just 1 or 2 events. There is some Lorentz violation theories that suggest high energy cosmic rays can come every now and again. But there's also, these things are sensitive to scalar dark matter. It could be a domain or boundary if it's somewhat beyond, it could be dark matter. main wall boundary or vortice. So we call this MAGE, multi-mode acoustic gravitational wave experiment, and my student drew this up. I think it looks pretty cool. And yeah, so we calibrated the second detector, it's all working. Here's an example of what the thermal noise looks like. It's pretty much if you look at the thermal noise, it's pretty much the mode temperature. It's the temperature of the surroundings. So that calibrates really well, and the experiment behaves very well, and we're seeing 2 events. So now we're using an FPGA. Each FPGA acts like 32 lock-ins. So now we don't need to buy 32 lock-in amplifiers. We just use one FPGA and it acts like 32 lock-ins. So we don't need them anymore from Stanford research. We've got a really good programmer from Liquid Instruments who works with us that designed this. So we're going to do 16 modes in each to try and get some information if we see another event. So we're currently taking data, and as I mentioned before, there's been papers coming out showing that these resonators are also sensitive to scalar dark matter, dilaton dark matter. We learned how to tune these recently too, so that could be useful if we wanted to start tuning them without doing these experiments. So the last thing there is one more thing to talk about, is quantum gravity. I won't talk about the Lorentz invariance experiments, but these are commutator deformation experiments where the commutator relationship might depend on mass, okay? So when we have a change in mass, you can get an extra term in your commutator relationship. I know Doug's done some work on this. So quantum mechanics is possible with macroscopic masses. Does mass modify the position of momentum commutator relationship? We've just got some new results. We're going to publish another paper soon. QG theories predict a nonlinear correction, and so we're looking at this nonlinear correction in our experiments. And can we test? And we can. We published this paper where we looked at the sapphire resonator and the quartz resonators, and we could put limits on this parameter in this commutator. And we know we can get down here. We've just done an experiment with the pores, which is going to put it down even further. We're going to get to here, which will be a paper coming out soon with my student. But we've just put in a grant application to try and get down to here. And so these minimum length scale theories, which get this generalized uncertainty principle. There seems to be a lot of work going on in this area at the moment, this generalized uncertainty principle. And we want to test this with our systems. And so what we test is this, when you've got this commutator relationship, the quasi motion of the harmonic oscillator gets this extra nonlinear term. That acts like a ducking nonlinearity. So we look for this ducking, this nonlinearity. That's what we do. That's an easier experiment to do. Here's a recent experiment where we can look for this nonlinearity, and if we don't see anything on the ordinary, we can put a new limit.
Is beta telling us the strength of the gravitational coupling that modifies the commutator?
Yeah, that's it. Yeah.
Okay.
Doug does some theory on this, he might know better how to explain it. So I'll finish there, and that's just a sort of really broad brush over some of the things we've done. Yeah, so thanks a lot.
Wow, that's a lot of stuff.
It's a buffet.
That's amazing. So, questions?
Oh, yeah. Well, this is, I guess, maybe not directly, but you had mentioned controlling for quantum noise. Is that something that's actually been done, or is just sort of hypothesizing because you're still looking at other constraints for it?
For which experiment's that?
Well,
Yeah, no, yeah, so what happens is, if we're doing a precision measurement, we're going to end up running into the quantum noise. So we call that the standard quantum limit. But it's only a limit, it's not necessary. If you're measuring something classical, it's not necessarily a limit. So what you have to do, there's ways you can go about it, because our Axion experiments is actually classical. And like gravity waves are classical, but you have to be so precise to see the effects of those classical systems that you run into the quantum noise of it. So then what you have to do is quantum metrology. And there's already Conrad Leonard in Boulder who's figured out how to do that for Axion. So where you squeeze, where you do basically a quantum non-demolition measurement, you put all your noise in one quadrature and read out the other quadrature. And that's what the gravity wave guys are proposing in the next run of LIGO. And we knew that when we was operating the bar, because I wanted to do that on our bar. Classically, it's called back action evasion. So you can avoid effects of back action of common noise. The common limit is just common noise, back action, and you measure. You put all the noise into the experiment when you're not measuring.
So you need to leave your system continuous long to monitor like a gravitational
Yes,
wave or
it's running.
like all year round? Or?
Well, the first time we ran for 153 days. This time we've just got it running, and we're going to run it for as long as possible and see if we see any events. If we see nothing, then we'll have not much to report. We'll just say we saw nothing. We're hoping to see some more events.
In one of the previous slides, you showed the interaction of various ions with, I forget what it was exactly.
With the paramagnetic ions with the photons?
Yes, there was an unknown there though.
Yes, there was an unknown that had a huge G factor. So it's probably rare earth.
Okay.
Yeah, because rare earths have very large G factors.
Okay.
But we didn't know what it was because there's not much rare earth study in South Island. As far as I know. It's all in YSO and other things. Yeah.
Did Joe ever actually detect anything?
Well, I once went to a conference with him in Pakistan in 1996, I believe it was, and according to him, he did. But I don't know. But I mean, he had all this stuff, he said, and proof, but no one ever really took it seriously.
Can anyone recreate?
What did he say it was? A nearby supernova?
Yeah, something like that, because there was there was also some gamma rays that correlated with these events. Yeah. I remember in that conference. What was interesting about Joe Weber, I'll tell you this story. So I would sit next to him at breakfast and dinner any chance I could get, just to listen to his stories, because he would tell stories about, because he was in the Second World War, being stranded on an island in the Pacific near Australia, and the monkeys throwing coconuts at him, and all the danger he got in and everything. It was really interesting. And then we had a midnight walk up a mountain in Nathia Gali, which I don't know if you can go there these days. But so we're walking up this mountain, and I'm talking to him, and then his foot slips, and he rolls about, I don't know, 3 meters down, or 3 feet down the hill a bit. All the guys besides himself, he's a famous professor, they got him up and that. And the next day when we were eating breakfast, he was telling everyone about the 30-foot drop he went down. So I then realized there's an order of magnitude exaggeration in all the stories. And I thought, they were really good and they were worth listening to, but there was always an order of magnitude exaggeration. I had the experimental evidence.
So the monkeys are questionable.
Huh?
The monkeys are questionable.
Yeah.
No one believed his results. But, I mean, Joseph Weber was an extraordinary physicist. He come up with this idea, and he was also very close to getting the Nobel Prize for the maser. He was one of the guys that first came out with that as well. Yeah, so there's some interesting stories that Ray has about that.
Oh, Ray knew?
Ray Chow.
Yeah,
because he
because
knows-
Towns ended up getting the Nobel Prize, and
Yeah.
Towns is Ray Chow's advisor.
Yeah, and but Weber was actually, according to he actually came up with it before him or something. Okay.
Towns scooped him,
Yes, somehow.
and Ray was the student involved.
The things, the gravitational waves they've detected so far are in the range of like frequencies of 300.
5 megahertz.
No. So the gravitational waves they detect
Oh,
in
yes.
LIGO
Yeah.
are like super low frequencies.
Yeah, that's right.
300, I mean, in the hundreds.
Yeah,
right?
that's right.
And so you're talking about like megahertz.
Megahertz, yeah.
So what can make?
Well, according to the people who work on LIGO, nothing. And it's not
Okay.
worth doing. When I put in a research grant, it was quite clearly they didn't want to fund it. So now so I had the research grant on gravity waves and the gut theory, and And they said, oh, that gut theory is really good. If you concentrate on that, we would have given you the money. But the gravity wave is not worth doing. So now I put in the grant. It's all about doing new experiments on quantum compound. And then one paragraph about gravity waves and scalar dark matter. Just revert, and hopefully they'll fund it this time. But they'll probably come up with another excuse.
So the Gertrudenstein or the inverse Gertrudenstein wouldn't make it possible, since we could, in theory, transduce between electromagnetic
Yeah,
and
it does make it
gravitational.
possible, but they just say there's no sources there.
I mean, like if we use an electromagnetic source in the lab, it will be in the megahertz or gigahertz
Oh
frequency.
yeah, but then you're generating very
Weak.
Yeah, very
Yeah.
weak, isn't it?
I mean, the Gertrude effect, basically, if you have like a magnetic field, you have a gravitational wave, it essentially like changes the magnetic field and
Yeah.
produces
Yeah.
radiation.
Yeah, this is the inverse effect.
To the inverse, so basically
Yeah.
take a,
Gravity wave going through a magnetic field produces photons.
right.
Yeah. Of the same, of a
Right.
comparable frequency,
Right.
right?
But then if you, so you're doing the inverse, you're taking
Yeah.
photons and
Yeah.
sending it.
It's called the inverse Gertrudenstein.
Okay.
Right.
But
Do you mind backing up just a few slides on the quantum gravity stuff? I noticed something about a forbidden, keep going a little more. There's something about for quantum gravity forbids a certain, right there. That bottom left figure, forbidden by quantum gravity proposals. Is there some bounds on the
I have no idea.
generalized
This
uncertainty?
is this guy's paper, Igor. You might know. I visited him in New Jersey.
And Aspelmeyer is well known in
Yeah,
gravity.
yeah, I know. But the first author is working in New Jersey.
So is there some sort of like bounds on the generalized uncertainty principle that is, that this forbidden region is referring to?
I have no idea.
So in other words, maybe there's already bounds on beta?
Yeah, probably. There's meant to be bounds of beta from pendulums, but they're a bit dodgy.
I think, so if you look at the red line, that's just the standard Heisenberg relationship.
Right.
And it's like a.
And then the blue is the modification.
That's the blue, so basically if the modification is true, I guess what they're saying is that region between the regular Heisenberg and the quantum, the gravitational one is not.
accessible,
Yeah,
because
accessible.
the quantization requires you to either be on the red or the blue, basically.
Right, so the blue line would be like a bound,
Uh-huh.
right? So basically, so you modify the uncertainty principle. So I mean, for example, like the regular uncertainty principle, you can't get anything like.
Yeah, it's the one,
Right.
inside that square root, the
Yeah.
one, right?
Yeah.
Yeah.
So, interesting, huh?
Yeah, I just never heard about quantum gravity proposals forbidding the values of
I
beta.
guess you have to read it.
The paper, yeah.
So if you're you can read it. I'll just put limits on the
No,
data.
I think what they're saying is that region of delta x, delta p space is forbidden. And there's not really, it's not about, beta is generally a parameter, right?
Yeah,
And so it could and in fact, if you look, notice the way they've done it, it's like beta naught over Planck mass squared.
yeah.
So and the c squared. So the thing is, beta is just a parameter of order unity, right? Well, that's the
Dimensionally.
idea. Actually it's dimensionless, right?
Yeah.
Because you've got delta p squared over basically a momentum squared, like m squared c squared. And so the idea is the correction should occur at the Planck scale, right? But there's some hope, like large extra dimension theories or blah blah blah, that basically for some reason beta is going to be a lot larger than you think, and then quantum gravity effects would show up sooner, right? But I mean, there are papers that basically put bounds on beta. So,
Oh, I see.
sorry, Mike.
You're the expert on the theory. I just putting limits.
Yeah. Any results experimentally in that area?
Yeah, we're going to have a new paper out.
Ah.
Yeah, which is better. It's better results. The students have been working on it with the boards, and we're putting in a grant to go down this path. Got to get money. Keep doing experiments and employ people, keep people employed.
How many hours you request your student to stay in the lab every week?
I don't request anything. They just stay if they want.
Oh, really?
Good.
I just say, have you done it yet? They go, no. Yes.
So it looked like you had a large number of students, right, in the last
Oh,
picture?
yeah, we're getting more and more students. Our university did this good thing. They started what they call frontier physics, which is an elite course. So you do a double major in physics and you need a certain grade to get in. And that attracted all the good students away from engineering and things like that into physics. And now, we have to extend them. So we've all done some extra stuff to extend them. I do a first year, so all these undergrads that come in first year that are in this advanced course, I now do a tabletop light shining through the wall experiment. So it's 2 cavities with the wall, asking can the light shine through, and if this certain type of dark matter exists, it interacts with the light. The light turns into dark matter, goes through the wall, then turns into a photon. And so I got this good animation where Luke Skywalker trying to shoot a laser through the wall but not succeeding, but Darth Vader interacting with the dark side of the Force and getting through and shooting some guy in the head. So
That sounds opposite though, because the stormtroopers always missed.
yeah, but there's not the dark matter. We're going from the dark side of the Force.
And of course, their armor doesn't work at all. Something of interest. Perth is, of course, at literally the ends of the earth.
Yes?
Fresno is rather isolated too. So I'm curious, where do your grad students and postdocs come from? And where do they go after you're done with them?
Okay, so all our students are local because we're the only really strong physics there. And so what I know is if we ever go, the physics world will lose access to a lot of good students. Because we get a lot of good students and they end up going somewhere else. I came from Melbourne. I did my PhD to work on, to go to Perth. I'm probably one of the only ones that left these coasts to go to Perth. The reason I did is because I had an experiment I wanted to do. I did electrical engineering. My science degree was applied mass and theoretical physics. I wanted to work in fundamental physics and use my engineering degree, and that was the best project I could find. That resonant bar project was unbelievable project. Yeah. That was really learned a lot on that. So I moved there for the project. The postdocs I get, I got a good group. We get a lot of Russians. We used to. And people from Europe tend to come to Australia. Americans don't come to Australia, but we get Europeans. But all our graduates, they all go off around the world. Get postdocs.
But most of your students are local.
Yes.
Did you just mention David Blair?
Yeah.
Is he the one that's also doing the superconducting Weber bar experiments now, getting higher sensitivity of like photon detection in there? Because I think we were actually looking at his particular experimental setup as a way to detect gravitational waves via superconductors. Is that the same Blair?
Well, there's only one Dave Blair I know.
Yeah, and that's the area he worked in, right? The Weber
Yeah.
bar area. So did he make them superconducting then? He went on from like what Weber did,
Yeah, they were always superconducting, niobium superconducting.
even with Weber?
Yeah, well, we had a niobium, so it would be superconducting, but we're looking at the acoustic resonance, but the readout was superconducting.
I see. I mean the bar itself.
Well, the bar will be superconducting because we cool it to 4 Kelvin and the transition temperature is 9.
So Weber's bars were also
No, they were
superconducting?
aluminium.
No, okay.
If they went below 1K, they would have been.
I see, yeah.
Other questions, comments?
This is a silly question, I guess, not really silly, but at the beginning, you said you had academics, postdocs, and students. What was the separation between academics and the
Well,
other two?
they've got permanent jobs.
Did what?
Permanent jobs.
Pete, I'm an
Good job.
academic. Mike's an academic.
Oh,
Ferraro's
so
an academic.
faculty.
Kate Chun's an academic.
Yeah. I was like, that sounds like
Nathan's
they're all
an
academics to me.
The postdocs don't have permanent jobs.
Okay.
All right, well, if there are no more questions, let's thank Dr. Tobar.